Hello and welcome to our Chapter 1 Atoms discussion. We are going to end this chapter with a little bit from Chapter E, which is Section 6, based off of energy. Today our discussion will contain when we start to classify matter, what is matter. We can dive into a couple of definitions of atoms and molecules. We'll be able to look at the scientific approach of how historically we came to where we are today and value and appreciate the work that scientists have done before us. We'll be able to talk about what a scientific law is, some theories, and we'll get into a couple of experiments that scientists did to help us understand how do we have this picture of what an atom is. So what I want to start us off with is this idea that chemistry, which you all are studying in this class, is the study of matter. How does it react? What does it look like? Where do we see it in nature? And so the idea of matter itself is what we have to start to dive into. And so when we think about matter and atoms, we're going to start with a definition for matter. Anything that occupies space. That's the first criteria. It has to have some sort of a volume with it. With that, it needs to also have mass, right? So we can think about macroscopic world things, a cup, a desk, a computer. We can also think subatomic things, a proton, a neutron. There might be smaller. They might be difficult to see with our own human eyes, but they are still classified as matter, this overarching idea, the realm of what chemistry studies. And so it doesn't matter how big or how small, but as long as it occupies space and has mass, we get to study it in chemistry, and we get to see what it looks like, what does it do, and things like that. So matter is composed of particles. These are some definitions from our textbook. Why I like to do some PowerPoint slides with these is so that we get the definitions down quicker. You can look these up in your textbook. You can read them from the PowerPoint slides provided for you. So matter, we're going to start focusing on that subatomic realm. Yes, we like to think about the macroscopic worlds, cars and desks and things like that, but chemistry is really looking at how things react, and to understand how matter reacts, we need to look at the subatomic realm. And so looking at it from the particulate point of view, matter is composed of particles. Neutrons, protons, electrons, that's what we're going to see in this chapter. How did we discover them? It's very exciting to think about where we've come from. In the past 100 years, we've learned so much in chemistry. And so that's where we are going to start our story, our history really of chemistry. Now, we've probably heard this a lot before. Structure dictates function. We're going to dive into that a lot. If you're from the biological realm or anything in biology, biochemistry, molecular science, things like that, we always kind of hear this saying, the structure dictates function. How the particles get together is very important. So we're going to look at that throughout this whole semester course. We're going to see what is the structure of the molecule, how did those atoms come together to make that molecule, and we'll see how that is dependent on almost anything. I like this statement though right here. How the particles come together dictates the physical properties of matter. We'll try to relate all of these things to things that we see in the observable world. Sometimes we might not be able to get that far, but we can at least see some sort of experiments that help us dive into matter. There's our definition that we talked about. Matter is anything that has mass and occupies space. So it has a mass and it has a volume. And we as chemists, we seek to understand. And that is what we're here to really dive into, especially in this chapter. How did the chemists coming before us develop all of these principles and theories that we have to learn about? And so, again, a couple of definitions, I apologize, but when we look at and start to communicate these things in these chapters, we really want to make sure that we're using the correct terminology. So atoms, basic submicroscopic particles that constitute a fundamental building block of ordinary matter. What does that mean? They're atoms. They're going to be things like hydrogen, helium, oxygen, the atoms themselves, right? So we'll think about, once we get into what makes up an atom, we'll think about this as just being the one element off of the periodic table, right? When we think about atoms, we can think one representation of an element. So when we look at our trusty periodic table, we are going to be able to see one representation of that element is what we call an atom. Now, a molecule is something very, very different. Substance is formed when two or more atoms come together in a bond. And we're going to be diving into bonds a little bit later. Section 2 is, or unit 2 is when we're going to be able to dive into those. But a molecule has to be more than one atom, two or more. And so when we think about whether we have an atom or a molecule, that really determines what we're talking about. If I talk about an atom of oxygen, I'm thinking of just one basic atom, oxygen, just like what I wrote up here. Now, oxygen can form in what we call a diatomic molecule. And that is very different than plain old oxygen by itself as an atom. So actually, when we think about the term oxygen, the name of the element, it's not very descriptive. And so thinking about oxygen atom versus oxygen molecule is what we're going to dive into and see what do we mean when we see these two things. Which one do we find in nature, right? Oxygen can also form into O3, which is ozone, and that's what we have a big discussion of in environmental chemistry. Part of my background is environmental science. A lot of my undergrad research was in the global climate change. And so when we think about all of these different types of representations of an element, we have to be able to know what we're discussing, right? All right, with the classification of matter, it's really important for us to be able to talk again about not only the name of the element that we're talking about, what form it's in, whether it's an atom or a molecule, but also the state and the composition that it's in. The state is simply going to be whether it is a solid, liquid, or gas. Those will be our phases. Another word for state is a phase. And that's what we're going to be able to see. Composition. Now, a composition is going to be very specific. It's going to be the type of particles we see. Mainly with composition, we're going to be seeing, is it pure or is it a mixture? And then we can classify a little bit more with that. Overall, the state is something that I think we're all a little bit familiar with. The state of matter changes from solid to liquid to gas as we increase temperature. So if we think about a solid, I use this diagram, we can add heat to an ice cube and make it turn into liquid water. If we add heat to a liquid, we can turn it into a gas, like water vapor. So knowing when a substance, whether it's an atom or a molecule, knowing whether it's a solid, liquid, or gas in a reaction can help us truly understand how is it reacting. Solids are very tightly packed. We see all of these solids bunched up together. And when we think about that, the ones in the middle might not be able to reach something on the outside, and the ones on the outside are exposed, right? So solids react differently than, say, a liquid. A liquid is a little bit more spaced out, right? So when we think about that liquid, we can see some spaces throughout that substance. Things can come in between, the molecules move a bit more. And then we come to gases, which gases, what we'll see in chapter 10, a couple weeks away from now, but in chapter 10, we'll see that gases are so spread out that they literally take the shape of their container, right? So they spread out as much as they can. And one of our theories that we're going to talk about in chapter 10, the kinetic molecular theory, helps us understand that gases act almost independently of one another. Solids and liquids, they're kind of packed together. They interact. They do some more things together. But gases, they're off on their own, doing whatever they want, very independent. So I like this picture because not only can we start to see the particulate diagram right there with the packedness, but we can see that solids have a very concrete shape, right, and a concrete volume. Liquids tend to take the shape of their container, but they're at least a fixed volume. And gases just spread out as much as possible. So when we think about all of these states, we can see that it is overall 3 different types of matter. So even though we can think about an ice cube melting to become liquid and then boiling to become a gas, a vapor, the actual molecule H2O is the same, but the reactivity and the physical properties of those solid liquids and gases are important for us to be able to discuss. When we want to talk about composition of matter comes with a variety of subcategories. The first thing that we want to think about with composition is, do we have one type of atom or one type of molecule in our sample? And so we can have a pure sample or a mixture. Now, a pure sample can have a couple of different definitions. We're going to talk about 2 main ones. A pure sample being an element, or it can be a compound. Compound and molecule are very similar. We're going to call them the same right now, so you can interchange those. Once we get into the type of bonding that we'll see in chapter 3 and 4, that's when we'll get to have something more specific. But for an element, one type of atom. So this could be something like neon. If I have a vessel of neon, a lot of chemistry experiments use inert gases, gases that don't react. Argon is another example of that. So when we think about gas tanks, we can think about those elements being just the atom itself. Now with a compound, think about that as being the definition of a molecule, 2 or more atoms. So I'm going to write that, 2 or more atoms bonded together. We still only have one molecule or one compound in our sample. It's still a pure sample. But those atoms are bonded together. So a sample of carbon dioxide gas could be pure, it could just be carbon dioxide. However, it is a molecule itself. Same thing with a sample of water, H2O. Now, notice for none of these compositions of pure or mixture, we won't see the idea of solid, liquid, or gas, right? Phase or state is one way to classify matter. Composition is another way. So they can work hand in hand. We can say we have a pure sample of neon gas, but the pure sample dictates the composition. The gas would dictate the actual state or phase. A mixture can be a homogeneous mixture, or it can be a heterogeneous mixture. For a homogeneous mixture, it is thoroughly mixed. Again, 2 or more compounds or 2 or more atoms not bonded. A mixture would be something that is like salt water. Salt water is a mixture of sodium chloride and H2O. Those aren't bonded together, but they are mixed thoroughly. We can think about the air. The air we breathe is partly oxygen gas, it's partly nitrogen gas, it's got some carbon dioxide in it. We have a little bit of helium and hydrogen floating out around there. So it's a mixture, but again, it's thoroughly mixed. We won't see things that we could pick out, right? A macroscopic world idea would be something like tea, or if you add things to your coffee. I like my coffee with a little bit of milk and a little bit of sugar, and I stir it up and it becomes a homogeneous mixture. I can't just take a sip and say, oh, that one was just the milk, or take a sip and be like, oh, that one was just sugar. It's all of it together, combined and thoroughly mixed. Heterogeneous, on the other hand, is not thoroughly mixed. So we get kind of like this cookie cutter, this side is more one thing and this side is more the other. The best thing that I can think about in a scientific example is the ocean. A lot of my undergrad research back in the day, a long time ago, was on the top 6 inches of the ocean, we see a lot of dissolved organic matter. We call it chromophoric dissolved organic matter. And this is mainly from plant runoff. It's a lot of issues with the degradation of soil and the degradation of plants. And then it gets into the ocean. And that dissolved organic matter can react with the sunlight to make small molecules that then go contribute to climate change. So the top of the ocean is quite different than the bottom of the ocean. And so we can think about that idea of the ocean is not a perfectly thorough mixed thing. Our ocean, closer to Orange, is Huntington Beach and Newport, which is quite different if we decide to go down to San Diego and hop in the ocean down there. Another example, trail mix. I'm a big camper and hiker. My family loves to go camping and hiking, and so we like to make snacks on the road, right? And trail mix is a great example of a heterogeneous mixture. When you think about all the things that you can put in it, whether it's dried cranberries or dried blueberries, you can have some cashews in there or almonds. Sometimes if you're like my mom, you put M&Ms in there. And if you're my son, you eat the M&Ms first because you can pick out the M&Ms. It's a heterogeneous mixture. It's not thoroughly mixed. Those are all great examples of how to decide the composition of matter. This chart is in your textbook. It's an awesome chart to be able to just look through some questions to ask yourself, just to decide elements, compounds, mixtures, and things like that. I like the particulate diagrams as well when we're looking at your textbook. Has beautiful, beautiful particulate drawings. Okay, moving on to the scientific approach. When we're looking at early ideas in chemistry, Lysippus was the first person to actually propose that matter was composed of what he called small indestructible particles. Plato and Aristotle did not really like this idea, so back in the day, this wasn't really held into any regard. But I think it's an interesting story that the book kind of dives in through. Today we have the scientific method, right? And we've hopefully all seen the scientific method in some way, shape, or form. Its two main ideas are observation and experimentation. When we decide to think about the scientific method, a good thing to think about are these two overarching ideas: observation. What do we see in nature? Can we create a hypothesis? A hypothesis doesn't hold much weight. It's just my opinion. It's a statement of my observations. It's maybe a prediction of what I think I'm gonna see tomorrow. The sun rose today in the east. I'm gonna maybe see that again tomorrow. That's a hypothesis. It has no backing, no experimentation, just my observation. With that, then we can experiment. And so with the experimentation, now we can start to develop an idea of data. We get data to back our observations, and we get to see what does that actually look like. Now, there are a couple of different types of data. We're not going to spend too much time on the scientific method. We want to get to the specific experiments that we see in our history. But scientific data can either be qualifiable or quantifiable. Qualifiable meaning describing how something happens, color, shape, smell, those are all qualifiable. Qualitative is the same idea there. Quantifiable is what we think of mostly when it comes to chemistry. Not that qualifiable is not valid. They're both very important for us, but quantifiable data is things that we get in the lab most of the time. Quantitative meaning we're measuring or quantifying something about the process itself. Subjective for qualifiable, meaning my opinion, right, is most often put into qualifiable things. If I think something's hot, you might say it's very hot. If I say it's really cold, you might say, well, it's not that cold, it's cool. So very subjective based off of the scientist. Quantifiable is objective. I get a number. It's 72 degrees outside, right? So we can see how temperature can be both qualifiable and quantifiable. What 72 means to you, hot, cold, cool, beautiful, is up to you. But the number 72 is quantifiable. Notice we'll have the use of equipment. Glassware balances instrumentation. To take a temperature, I need a thermometer. And I need units. Is it Fahrenheit? Is it Celsius? Is it Kelvin? We'll be able to look at quantifiable data a little bit more in this class. Now, the early ideas, who came up with a lot of these things. One of the big name players that we'll see a lot repeated over the course of the semester is John Dalton. He was the first to offer convincing evidence to the discussion of matter is created by small particles idea. So he developed the atomic theory of matter. We'll talk about that in just a second. We'll also talk about the atomic theory and its laws. The laws came first and then the atomic theory. So we'll define a few things about laws versus theories. We'll look specifically at the first two here: the law of conservation of mass and the law of definite proportions. The law of multiple proportions is good too, but we won't spend too much time on it. All right, for the law of conservation of mass, this law states that matter cannot be created nor destroyed. Matter can be transferred, though. So I'm going to write that. What this means is that I can't go into the lab and expect to create matter out of thin air, right? I take some reactants, I can transfer them to different molecules that are my products. But in order to satisfy the law of conservation of mass, I have what we call a balanced equation. Now, Antoine Lavoisier, who is one of my absolute favorite chemists, I'll tell you why in just a second. Antoine Lavoisier was a French chemist. He lived from about 1743 to 1794. You do not need to know those dates. Those dates are just for you to appreciate. We're painting a picture right now of where we came from, you know, what we can think about in the 1700s. In America, we think about, you know, the Revolutionary War, but what else was happening in the world, right? So Antoine Lavoisier was a French chemist, and he studied combustion. The guy, why I love him, is he studied reactions that blow up. Like, how cool is that? Combustion reactions, in general, you take some sort of a fuel, which is usually a hydrocarbon. Hydrocarbons, meaning it has hydrogen and carbon in it. You react it with oxygen gas. I'm going to put a little G there. That tells you the state of the matter, right? And you create carbon dioxide gas and water vapor, H2O gas. All of those being the state, helping identify the classification of matter. Fuels can be gases, they can be solids, they can be liquids. Most often, we're going to see gases. We can think about propane. That's a hydrocarbon. It's got 3 carbons and 8 oxygens. We can think about butane. That's 4 carbons and then 10 hydrogens. When we think about methane, CH4, 1 carbon, 4 hydrogens. Those are all great organic fuels. I'm an organic chemist by degree, so I'm a little biased to those types of fuels. There are other types of fuels out there, but we try to keep it as simple as possible. Now, with combustion, Antoine Lavoisier did a couple of very important experiments. And namely, what he did was he studied combustion with careful measurements of the mass of all of the objects over here. These are called the reactants. Sometimes those are called the starting materials. They're the things on the left. It's what we start with. And he measured those very precisely, right? He can have their mass in grams or milligrams, whatever he decided. And then he reacted them to form the products. What we end up with. And when Lavoisier measured the reactants and compared it to the measurement of mass of the products, what he noticed was that they were the exact same. And so he went through the scientific method in order to say, my observation was that mass is consistent in a reaction. He hypothesized that the fuel mixes with oxygen to form the products. That wasn't understood yet. In the mid-1700s, we didn't really know about reactions, which is mind-boggling and really fun to think about. He knew that something changed. He knew that whether he started with a liquid or a solid or a gas fuel, something happened because heat was also expelled. Combustion reactions, blowing stuff up, you know that's going to be an explosion. We know that now, but Lavoisier was simply just observing that. And then he developed his experiment. And that experiment generated this data. And the data said the mass of the reactants is always going to be equal to the mass of the products. Super amazing to start seeing this development of our scientific method with Lavoisier and his study of combustion. A hypothesis, again, is just a tentative interpretation of an observation. He didn't quite get to the law yet. It's not until you actually get to data. So let's scroll down here and say, lots of data. Then you can start to generate a law. Now, what is a law? A scientific law is readily tested. It is not something that is truth. I don't want us to think truth. Scientific law is a brief statement we'll say that summarizes past observations and predicts future ones. So the law of conservation of mass says this. We'll scroll back up there. Matter cannot be created nor destroyed, but it can be transferred. We can see that every single time we do a reaction. In the past, Lavoisier measured the mass of the reactants, he did the reaction, and he measured the mass of the products. And the data shows that the mass is the same for the reactants as was the products. So no matter was lost and no matter was gained, it's always consistent. I predict, based off of this law, that any other reaction that I do from here on out will be conserving mass. The mass of the reactants should be equal to the mass of the products. Now, a theory is something quite different. A theory is something that takes all of the law and all of the data with the law, and it creates a model, that model for the way that nature is, and it tries to explain that. It can be a collection of laws, but the main thing that we want to think about with this collection of laws is the idea that a theory explains how nature behaves. Notice in the law of conservation of mass, it just says this is what's going to happen. It doesn't tell you how. It doesn't tell you why. It just says this is what's going to happen. It's a statement that summarizes the observation. A theory takes all of our observations, it takes all of our predictions, and it helps explain why we see what we see. It explains how does this reaction react in order to understand why mass is conserved. So we'll dive into a couple of more laws, and then we'll get into Dalton's atomic theory. All right, the law of definite proportions was developed by a man named Joseph Proust. He was also a French guy in the late 1700s. Lots of things happening in this time period. He summarized the law of definite proportions this way. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. What does that mean? H2O is H2O, no matter where you get it. What we call water will always be one oxygen, and two hydrogens. That little 2 subscript goes to the number of hydrogens. 2 H's to 1 O. Let's put those in little brackets. 2 hydrogens to 1 oxygen. Now, We know that today. We're like, well, yeah, Lauren, duh. They didn't understand that in the late 1700s. We didn't have these molecular formulas like we do today. And so when we think about the law of definite proportions, it's something that might seem silly, but in the big grand picture, we're looking at the 1800s and not knowing the actual proportions of elements in the given compound or in the given molecule. So when we think about the law of definite proportions, it's literally saying when I have a name for something like water, that water is established with a specific ratio of elements. And I can't change it. If I change it, H2O2, I have something different. I don't have water anymore. I have what we call hydrogen peroxide. Where the ratio is 2 H's to 2 oxygens, right? Different ratio, different molecule. So as we are diving into the law of definite proportions, we can see this in experimental techniques as well. Joseph Proust studied mainly decomposition reactions, and in a decomposition reaction, we take one molecule and it reacts with itself to just decompose into its constituent elements. Constituent meaning just what it is made up of. Kind of what we did with those ratios up there. One water molecule breaks up into 2 hydrogens and 1 oxygen atom, right? Constituent elements or atoms. A couple of different examples we can see here with mass data. And this is how Joseph Proust was able to do it. The decomposition of 18 grams of water always resulted in a 16 gram to 2 gram ratio of hydrogen to oxygen. Now, when we think about that reaction, hydrogen and oxygen, we'll discuss later why there's those subscripts too. They form diatomic gases in nature, and we'll talk about that a little later. We'll also learn about balancing equations in just a little bit. But what the law, this example of for the law of definite proportions tells us is that if I had 16 grams of oxygen to 2 grams of hydrogen, that ratio of 8 grams of oxygen to 1 gram of hydrogen, I just reduced it there, will be consistent no matter the sample, right? So let's just pretend that I had, 36 grams of water. It will decompose every single time to 32 grams of oxygen and 4 grams of hydrogen. And the reason for that is because of the ratio. Still an 8 to 1. Gonna be consistent. The constituent elements will always be in a fixed ratio. Now, here's a type of example of a question that you could see on an exam. 2 samples of carbon dioxide decompose into its constituent elements. One sample produces 25.6 grams of oxygen. The other produces of oxygen and 9.6 grams of carbon. The other produces 21.6 grams of oxygen and 8.1 grams of carbon. Show that these results are consistent with the law of definite proportions. Are they the same molecule originally? Well, let's take and do the ratio. Oxygen to carbon, or you could do carbon to oxygen. It doesn't matter which one you put on top. But this way tells us that there is a 2.67 to 1 ratio of oxygen to carbon. Wonderful. Doesn't need to be a whole number yet. These are just masses. Let's do it again. 21.6 grams with the other sample, 8.10 grams of carbon. And what we can see in that ratio is the same exact 2.67 of oxygen over 1 carbon. That ratio is consistent. Yes, law of conservation or law of definite proportions there. Now, the law of multiple proportions is where we can get into a little bit more detail of molecules. We won't spend too much time on the law of multiple proportions, but what it clearly just states is that if there are different, if a molecule slash sample has a different mass ratio of constituent elements, it's a different compound. Kind of what we were hinting towards with H2O and H2O2. H2O versus H2O2, both consisting of hydrogen and oxygen, but in a different ratio. And that's what we have to say is water versus hydrogen peroxide are different. They'll have different properties, they'll have different reactivities, and that's what the law of multiple proportions just says. We'll see that in a couple of other ways too. Carbon with 1 carbon versus carbon, with 2 carbons, right? Carbon and hydrogen can go and create a bunch of different things. And so when we're thinking about the law of multiple proportions, it simply just states just because you are created with hydrogen and oxygen, you don't necessarily have to be water. You could be a bunch of other different things too with different mass ratios. Now, John Dalton took all of this and developed his atomic theory. And what John Dalton's atomic theory explains are these 4 postulates. Now, it took the laws that we just kind of learned about and it created a theory. Now, these postulates are what he thought were a good introductory explanation of how matter behaves. But again, we'll get into the why and the how throughout the next 2 or 3 chapters. Postulates are just statements of what the theory talks about. The first one says that each element is composed of tiny, indestructible particles called atoms. That's what he developed. The second one, all atoms of a given element have the same mass and other properties that distinguish them from other elements and atoms of other elements. So this looks at, the law of definite proportions. A little bit also in terms of the law of multiple proportions. We'll get into some of the issues with these in just a second, but 3 says atoms combine in simple whole number ratios to form compounds. Wonderful, that's again the law of definite proportions. And atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms change only the way that they are bound together with other atoms. This is the law of conservation of mass. Now he took these and he broadened the laws and he changed the definitions to fit his theory. A couple of issues with these that we see now. Number 2, Not all atoms of a given element have the same mass and other properties. We're going to dive into next time isotopes. Isotopes are an issue. We'll define those in the next lecture. And number 4, a little issue here. Nuclear reactions we know now exist. We're not going to talk about nuclear reactions. They are amazing. I did work for a short time, for 4 years before I decided to go into teaching. I worked for Southern California Edison, who had a nuclear plant off the coast of San Onofre. And that those nuclear reactions, an element can decompose into smaller elements, releasing all sorts of different types of things. We can see that elements do decompose and can break down. So elements are not technically indestructible in a reaction. They are indestructible by our idea of just a basic atom. But in nuclear reactions, we can make them decompose, which is very, very interesting. Now, the discovery of the electron was J.J. Thomson, late 1800s. So we've moved quite a far distance away from our idea of when we looked at what we were just looking at with the laws and the development of the laws. J.J. Thomson was the first to observe that a beam of particles called a cathode ray traveled from a negatively charged electrode, called a cathode, to the positively charged end, called the anode. That's very important to be able to say negative versus positive, right? That flow told us that he was discovering the electron. We'll get in there in just a second when we see a picture. The particles that composed the cathode ray had the following properties. They traveled in a straight line, they were independent of the composition of the material from which they were originated, the cathode, and they carried a negative electric charge. How did he know that? Because they originated at the cathode and they traveled towards the anode. So that negative little charge, that's my abbreviation for the electron, E with a little negative charge up there, was one of the observations that he had. Now, what you would really want to get out from these discoveries, these are all observations, right? They're all observations. You can get an experiment to then collect data. J.J. Thomson was able to measure the charge to mass ratio of the cathode ray by deflecting them using electric and magnetic fields. He was able to get this value, negative charge being the electron, negative 1.76 times 10 to the 8 coulombs, which is an electrical charge, per gram. So this is a charge to mass ratio. Notice charge in coulombs per gram divided by grams. Now, that data was developed by this type of an experiment. This is a normal cathode ray up here. It's connected to a high voltage battery inside this beautiful glass tube, hand blown at the time, right? When we think about what's inside of there, it's partially evacuated so that there's no air resistance. And the electrons always traveled from the cathode to the anode. What J.J. Thomson did was he made this bottom alternate cathode ray type of experiment. Here's the general start, right? Here's that general anode and cathode that we saw up there. And what he did was he put a little hole through the anode so that the electrons could pass right through. And so undeflected, they went right back through to a detector, probably photo paper. We'll talk a little bit more about the ways of detecting a little later on. Not super important, just fun tidbits of knowledge. But what he was able to do was take these electrically charged plates and a magnet and start to bend the actual beam in the backside of this evacuated tube. He kind of made it like a balloon shape. so that he could deflect. And the deflected beams, he was able to actually measure the amount of deflection, the mass of the charge to mass ratio. Notice for his experiment, that charge to mass ratio, he was not able to find the actual charge or the mass itself, just the ratio. And that was it. Now, what he was able to take for us was the idea that the electron was negatively charged. And it was a low mass particle. The charge, negative 1.67 times 10 to the 8 coulombs per gram. That idea tells us the numerator is very, very big. The denominator is very, very small. So the electron mass itself was small, smaller than any other atom that he had that was discovered at the time. And so that idea of being negatively charged, he started to identify the properties of electric charges. Opposites attract. A positive and a negative come together, right? Like charges repel. So two positives putting together would repel each other. The arrows go opposite. Say opposites attract. Two electrons, two negatively charged things, repel each other. But when we take a positive and a negative and put them together, overall they attract each other because the exact same magnitude, right? But when combined, they have a zero sum. And so J.J. Thomson was hypothesizing that the zero sum was some sort of a driving force for those two things to come together. From the J.J. Thomson experiment, Millikan came by. Now, Robert Millikan was at the University of Chicago. In 1909 was when he did his experiment. Late 1800s for J.J. Thomson. He was working out of Cambridge. And so probably about 10 to 15 years after the original cathode ray experiment, Millikan decided to do a drop oil experiment, or an oil drop experiment, to determine the charge of the electron. That's what he ended up finding, was the charge of the electron. From his data, he was able to deduce that single charge by measuring the strength of an electric field that it was required to halt a free fall of an oil drop. Now, if we look at this atomizer over here, I want you to think about early 1900s. It was probably like a perfume bottle type idea. I can imagine if you have been on campus before and been to the Orange Circle, you've walked through maybe some old stores with these, like, you know, like the retro stores where we're looking at a perfume bottle that's spraying a fine mist of oil, right? That's what we have. Atomizers now that are a little bit more high tech than this, but at the end of the day, he had a whole bunch of dots up in this upper cavern. Now what happens is he had a tiny little slit in the middle of that positively charged plate so that the oil drops could go down one at a time. Now, he had some ionizing radiation, probably X-rays, that he was able to pinpoint right at that one electron. He had a light source so that he could just view it. Here he was standing over here, probably getting cancer from that ionizing radiation. Sad day, but still, that's life. And so the negatively charged plate, he understood that opposites repel, so negatively charged plate and negatively charged electron, they were able to repel each other at a specific charge of the negatively charged plate. And so what he wanted that one tiny little oil droplet to do was be suspended in an electric field, stop, hover. And that's what he was able to decipher. He deciphered that the charge of the oil drop, sorry, my exponents are being tricky here. He saw that the charge of the oil drop was always floating and whole number multiples of negative 1.6 times 10 to the negative 19 coulombs. And so that's what he determined was the single charge of an electron. Pretty awesome. From there, he was able to do stoichiometry to figure out the actual charge or the actual mass of the electron. So when we're looking at what he took from the charge to mass ratio was that he found the charge first and then was able to deduce the mass after that. That negative 1.60 times 10 to the negative 19 coulombs per electron times our negative 1.67 times 10 to the 8, whoops, flip it, coulombs per 1 gram. We were able, with Millikan's experiment, to find out what the actual mass of the electron was. Very, very small number, but what we get to see from this calculation is the idea that the conversion factor given from J.J. Thomson was able to look at individual portions of the electron, whether it was the mass or whether it was the charge. Very, very small. Now, when we think about the charge or the mass of the electron, Millikan was not that far off. I think we take about 9.1 times 10 to the negative 28. And when we think about that times 10 to the negative 28, that is a very, very small number too. So to be off by a tiny little bit with this experiment, which I look at as kind of like a shoebox looking in with a perfume sprayer, he did a very good job. Very, very good scientific experiment there. So what we developed, we know that there are electrons. There are other protons. We were able to develop that too. That is not as well understood in terms of who developed it first. So we won't go into those experiments. But this is a very, very interesting fact right here. The plum pudding model was accepted in the early 1900s, excuse me. The plum pudding model is an early 1900s idea of what an atom looked like. Plum pudding, if you don't know, was a popular Christmas dish in England at the time, early 1900s. And what plum pudding was essentially our version of a fruit cake, if you've ever seen a fruit cake, where you take a whole bunch of different components, you just mix them all up together and you bake it and you hope for the best. So the early structure of the atom was this idea that protons and electrons were all just kind of swarming together, no big deal in this plum pudding model. We now know that is not true. What came after this was the Rutherford gold experiment. 1909, Ernest Rutherford, who was working under J.J. Thomson at Cambridge, had subscribed to the plum pudding model, and he was performing an experiment to confirm this. This is what's great about hypotheses. You might have one, and it turns out to be the exact opposite of what you think it is. The gold foil experiment that Rutherford used, why not gold foil? He put some gold foil right in the middle, very, very thin piece, and he was able to take lead around a source of alpha particles. So again, nuclear experiments. An alpha particle is a helium nucleus. Just a helium nucleus right there. No electrons in that helium atom, just the nucleus itself. And those alpha particles being positively charged then, he was expecting a few to deflect, and he was expecting this idea of, oh, let's try to confirm the plum pudding model. So he got his alpha particles, most likely from Marie Curie and other scientists in the day that were dealing with radioactivity, particle emissions from unstable atoms. And he did this experiment, and what he noted was that the experiment, most of the particles passed directly through. He was not expecting that. He was expecting a lot of things to bounce off. And what he looked at was the idea that, well, if there was an actual deflection, that maybe right in the middle there, you can kind of see it if I zoom in, a tiny little nucleus. And the protons and the neutrons must be encased in that tiny little nucleus. And so the positively charged species were a lot more dense than what he thought. It's amazing to think about the early 1900s, 100 years ago, give or take 10 years, 110 years ago, we did not know about the nucleus. Incredible, crazy. All right, more nuclear theory. We developed the idea of the nucleus. Most of the atom's mass is in the nucleus. That's where protons and neutrons are. P with a little plus sign and N with a little N, a little zero is a proton and a neutron for me. Most of the volume is empty space. So electrons are dispersed throughout the majority of the volume, but the protons and the neutrons are encased in the center. We'll talk a lot about the electron cloud as we move into chapter 2. What we also get from this was that the Rutherford model was highly successful, but it did not count for the mass of the neutron yet. That wasn't until 1932. Look at that year, 1932. A student of Rutherford's, James Chadwick, demonstrated the unaccounted mass was for neutrons, neutrally charged particles. The neutron has a mass that is similar to that of the proton, but it has no electric charge. That is less than 100 years old. Crazy to think. So here we go. Protons are protons, neutrons, and electrons. The mass of the proton has nearly a consistent mass with that of the neutron. Let me just get those exponents up there. 1.67 times 10 to the negative 27 kilograms. The upheld mass of our electron in kilograms is 9.1 times 10 to the negative 31 kilograms, about 1,000 times lighter for that electron. So that's why we don't really account for the mass of the electron when we talk about the mass of an atom. We're only going to be looking at the protons and the neutrons. This chart is a beautiful chart to have just organized in our thoughts. Mass in kilograms is our standard SI unit. But we don't really work well with that in chemistry when we're talking about the theoretical. So we do have the idea of the atomic mass unit, the AMU. And so we have normalized the mass in kilograms to an AMU. 1 AMU for a proton, 1 AMU for a neutron, and effectively 0 for the electron. We also see the relative charge of the proton, neutron, and electron. There was a calculated charge in coulombs, which is again an SI unit, but again relative for us. Instead of having that 1.6 times 10 to the negative 19 as the charge in coulombs, we'd rather have just a relative charge. So the numbers that we will use most often are the AMU units and the relative charge units. The relative charge is a unitless value, +1 for the proton, -1 for the electron, and 0 for the neutron. Now with our atomic mass unit, or AMU, it's important to be able to say, why do we use it? What's the purpose? And the purpose is, one, to show the actual drastic difference between the proton, neutron, and the electron mass. And it also helps simplify our calculations. Sometimes it's abbreviated AMU or just simply U. What we'll see a lot in chemistry is the idea that we're really, really lazy. Chemists like to abbreviate things as much as possible. And so the atomic mass unit is our first type of way of normalizing a mass to better suit our needs. Specifically our needs of looking at the subatomic realm without going so drastic, 10 to the negative 27 kilograms. There's no way we're going to measure that on a scale. So we'll see, again, as we dive into this video, we'll see how we actually can measure things in the lab, but most often in our theoretical purposes, the mass in AMU will suffice. Okay, some atomic symbol notation. what can we do with that information of the subatomic particles? Well, the proton count itself defines the element. Proton count is the most important factor in defining what atom or element we are working with. And that is what we call the atomic number. We're going to have a couple of definitions here as we get through understanding how we write out elements in our shorthand way. Atomic number, or even abbreviated the Z, it could be referred to as the nuclear charge. We do know that in the nucleus we have protons and neutrons. The mass, protons and neutrons, are contained in a very small, highly packed, dense section of the actual atomic structure. That's what Rutherford's gold experiment determined. And so when we think about that nucleus, it contains protons and neutrons. The protons being the only thing that is charged, so we can call it a nuclear charge. That doesn't mean that the neutrons are not important. Neutrons are still important. However, the charge itself of the nucleus only comes from those particles in the nucleus that are charged, which are the protons. We can write an elemental symbol as X. And from that elemental symbol, we can get a name. We'll talk about those in just a second. If we wanted to write a little bit more expression there, we could put Z in the bottom left-hand corner. That's the atomic number, the number of protons. We can also write at the top left-hand corner A. So another definition we have here is the actual mass number, which is actually defined as the protons plus the neutrons. What is the mass of the atom that we are looking at? Right, so Z is our number of protons, A is our mass number, the protons and the neutrons. The chemical symbol is always linked with our Z, our atomic number. You can't change one. If I say, what's atomic number 1 on the periodic table, it always has to be hydrogen. If I say, what's atomic number 6, it always has to be carbon. Proton count changes, atom changes. So we usually never see the proton count change in a general chemistry class because we're not going to deal with nuclear chemistry. Very, very interesting topic. Love to discuss that with you if you want to know about it, but it's not under our course curriculum. The mass number can change, and we'll be able to discuss how does the mass number change. It won't be because of the protons, it will be because of the neutrons. Another way to write a shorthand atomic symbol notation is by writing the symbol dash the mass. Because the atomic number and the symbol are linked, you don't often have to write Z anywhere. It's optional. You should know based off of the symbol how many protons are in that element, but the mass can change, and that's based off of our neutrons. And so when we're looking at a couple of different ways to write out some informational tidbits on our atomic symbol notation, we could see either one of these. So for instance, we could see chlorine 37 right there. When we think about chlorine, we can look up on a periodic table and see, oh yeah, chlorine right there is atomic number 17. We don't have to write it, because I would know just by looking at that atomic symbol, the proton count is 17. This is a neutral element, so I have to be balanced with my protons and my electrons. And my neutron count, I would simply take the mass minus the number of protons to solve for that. So we can look at that atomic symbol notation that said Cl37 up there and know a lot about the element that we are discussing. Another way to write that would be Cl-37. You will always have a periodic table with you. I do not need you to memorize this beautiful, beautiful thing. We will dive into the periodic table more and its structure and how Dmitry Mendeleev, a Russian scientist, developed the periodic table just over 150 years ago. But at this point, we just want to be able to look at it, to find some important information, see what's on here. So a couple of things that we can look at. I'm just going to bring up hydrogen right over here. What we see in this box up for hydrogen is that it has a little 1 up there. That is the atomic number. Notice how the periodic table is organized by atomic number. If we read how we normally have read, left to right and top to bottom, 1, 2, 3, 4, 5, 6, 7, 8, all the way down to 118, which was one that was newly discovered in the past year. Now, yes, the structure of this periodic table might look a little weird. Why are there some gaps? We will dive into that in just a couple of lectures, and we'll see all of the wonderful things that we can deal with. Notice down here, right there, it says underneath the name hydrogen, it says 1.01. Now that is not the mass number. The periodic table does not contain mass numbers. What it does contain is an average isotopic mass. This mass is in AMUs. We aren't looking at these masses as kilograms. They are in the atomic mass unit itself. But what's important to be able to note is it's not a whole number like our mass numbers. Mass numbers are whole numbers. To a point, what we want to think about is when we are looking at our atomic symbol notation, and the mass number itself is the simplistic value of protons plus neutrons, an average isotopic mass introduces our new discussion of isotopes. Now, this is where we have to say, sorry, John Dalton, one of your postulates was not correct. If we remember postulate number 2, I believe, it said, or maybe it was number 1, whatever postulate it was, it said that every element, no matter what sample, has the same mass and same exact properties. Well, that's not true anymore because we have isotopes. Isotopes are varying numbers of neutrons. And when different elements have different numbers of neutrons, they could have the same proton count. I'll give you a couple of examples in just a second, but those relative number of neutrons could be different, and it actually changes the mass, it changes the physical properties, it changes everything about the element. Now, the most important example, H1 versus H2 versus H3. Hydrogen actually has 3 isotopes. The most common one that we use is H1, where there is 1 proton and no neutrons. So the mass number is 1 and the atomic number is 1. So 1 proton, no neutrons. Bummer. For H2, atomic number is still 1, but now the mass number is 2. So we know that we have 1 proton and 1 neutron. With H3, atomic number is still 1, mass number is 3. So we know we have 1 proton and 2 neutrons. Now, what's interesting about hydrogen, the most abundant hydrogen that we see is H1. H3, tritium, has a special name for it. H2 is deuterium, H3 is tritium. Tritium is actually radioactive. Pretty crazy. So it's not abundant in nature, but it does exist. We can make hydrogen 1, H1, a radioactive species by pummeling it with some neutrons. 2 of them latch onto the nuclei and we make tritium, H3. Just a couple of different tidbits. You don't need to know about the specific properties, but you should know that all elements have the possibility of varying their neutrons, and so all elements have the possibility of having isotopes. Now, what does that mean for us? Well, the periodic table was set up with the isotopic average mass and not the mass number, because what we see in nature and in any given sample is there's some of everything. Neon 20, neon 21, and neon 22 are all abundant in nature. And so what we see on the periodic table, if I can just slide back up for us, for neon right there, neon has an average atomic mass of 20.18 AMU. Well, that makes kind of sense. When we go back down to our natural abundance there, the percentage, there is a majority of neon 20. Okay, but we shouldn't use 20, the mass number, in any of our calculations when we're in the lab, because any sample of neon has 90% of neon 20, but 10% of neon 20 and 21 and 22. So our calculations would be off. So whenever we do a calculation in the lab, we want to use the average atomic mass, the one that includes all of the isotopic abundances that we see. So these abundances are really special. They are determined based off of an instrument called the mass spectrometer. We won't be diving into the mass spectrometer. It is in your textbook. You are more than welcome to read about it, but I don't need you to do any calculations with determining natural abundance. What I would rather you be able to do is calculate the average atomic mass based off of those given abundances. So for instance, we're going to see how to calculate the average atomic mass. It's with using this style calculation. Here is the formula. Atomic mass is equal to sigma, which is the sum of all of the masses times their abundance, their natural abundance. So if you have 2 isotopes in a given element or 3, you times each mass by its own abundance and then add up each of those. So an example, chlorine 35 has a mass very, very close to 35. We're trying to be as specific as possible with our data. So we'll give you the actual data that we would see from a mass spectrometer. And the abundance, or the isotopic abundance, which is always given in a percentage, 75.77%. Now, chlorine 37 is also an isotope of chlorine. It has a mass of 36.97 AMU and an abundance of 24.23%. When we want to plug these in to the calculation, it is very important to take each step-by-step calculation. We would take the mass of chlorine 35 and multiply it by its abundance. Now, we don't want a percentage at the end of the day. We want our units to be in AMU. So change that percentage to a decimal point. Then we'll do the same for chlorine 37. Now, if you've taken this class before, or you watched the intro video to significant figures, you know that when we have different orders of operations here and different mathematical operations such as multiplication and addition, we need to take one step at a time in order to truly understand what sig figs we have. So I'm going to do the multiplication first, 4 sig figs and 4 sig figs. So my answer here should be 4 sig figs. 26.50 AMU plus, again, 4 sig figs and 4 sig figs, 8.958 AMU. Now, when I'm changing my operation to addition, I need to remember when adding, I don't look at the number of sig figs, I actually look at the number of decimal places. And that's how many I need to report the smallest amount. So I have 2 decimal places adding up with 3 decimal places. So my value should only have 2 decimal places. I'm only as accurate and precise as my data. So there is our calculated atomic mass for chlorine. Not chlorine 35, not chlorine 37, average atomic mass for chlorine element. Let's go back and let's check. There it is. Now, these numbers do get updated on a regular basis. People are doing more accurate techniques to determine the actual average abundances of isotopes. So don't be alarmed if the periodic table you have is slightly off. We are calculating based off of the most relevant numbers that we see, not trying to match it perfectly to the periodic table. All right, so that's why it's important to be able to use this value on the periodic table and to be able to calculate it from given data. I have a slide that goes through that on the atomic mass problem. If you want to step it through again, feel free to. We'll do more in class together. All right, another unit that we can deal with, this is the SI unit for amount, the mole. It's the second and more fundamental thing to understand about the mole is how to get its specific value. Now, what is a mole? Now, a mole I like to think about as a dozen. What is a dozen? Well, it's 12 of something, right? The mole is like a chemist's dozen. It tells you an amount of something. Now, when we're trying to think about the biggest problem in chemistry, it's moving from the subatomic realm to the real world, the macroscopic realm. How do we connect something like an AMU to a kilogram? It's really hard. 1 AMU is somewhere around 10 to the negative 27 kilograms. We can't measure that mass in the lab. So how do we connect it? And the answer to that is the mole. This handsome guy right here. Avogadro was the first scientist to actually investigate the actual number of particles in a sample. Amedeo Avogadro was from Italy. He was born in the late 1700s in Italy. He went to the University of Turin, and when he developed his idea of the mole as a way of counting atoms and relating it to mass, people actually didn't take him seriously. We're going to see that repeated a lot in this class. And it wasn't until 4 or 5 years after his death that people really started to understand, wow, this was important. The mole is how we connect the laboratory scale to the subatomic scale. And the exact value of the mole is equal to the number of atoms exactly in 12 grams of pure carbon-12. Why carbon? Well, me being an organic chemist, I'm biased to carbon, but think back way back when Avogadro was doing these experimentations with determining the mole. Carbon was readily available. It was often used already in combustion reactions. And so a lot of people were already working with carbon. And carbon-12 is the most abundant isotope of carbon. And there was just a lot of it around. The other isotope of carbon that is naturally occurring is carbon-13, but it's really only about 1% of carbon is carbon-13. There is such a thing as carbon-14 dating. However, that is very, very small amounts, and so that's not in this discussion or usually ever in calculations with finding any sort of average atomic mass of carbon. So most abundant element, carbon. Most abundant isotope of carbon, carbon-12. So exactly 12 grams of carbon is equal to 1 mole. And Avogadro determined that that is 6.022 times 10 to the 23rd carbon atoms. This is where we get the value N sub A, or Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd particles per mole. I'm going to change it to particles here. The reason for that is so that we can understand this isn't just related to carbon. Yes, it was based off of carbon because of the reasons we stated earlier. However, it doesn't mean that it only applies to carbon. It applies to anything. So you could have a mole of donuts. Yeah, I want a mole of donuts. Screw that 12. I don't want a dozen. I want a mole. I want 6.022 times 10 to the 23rd donuts. That's a mole of donuts, right? We can do any type of particle. It can be atoms. It could be particles like protons or electrons. It could be a molecule. It could be something like CH4, right? I want a mole of CH4, the molecule, methane. That would be 6.022 times 10 to the 23rd molecules of methane. So this number is very, very useful. What it also does for us is it gives us a new conversion factor between particles and grams. And that mole is that idea that links us into the atomic realm. The AMU, the atomic mass unit, can now be defined as a ratio. 1 AMU will be equal to 1 gram per mole. That is highly useful for us because now we can use all of those AMUs on the periodic table, the average atomic masses, and say, okay, we just calculated chlorine's atomic mass. And that atomic mass was 35.45 AMUs. But what we can do now is take that number into the lab. It's so exciting, 35.45 grams per 1 mole of chlorine. So that is very, very useful for us. Just a couple of practice calculations so we can see it. Calculating the number of copper atoms in 2.45 moles of copper. How we would set that up, 2.45 moles is our given value. We would use Avogadro's number. Now remember, when we are converting between one unit to another, we always want our desired unit in the numerator and our current unit in the denominator. What that does for us is it allows us to actually cancel or cross cancel between the numerator and the denominator, and our current unit, which is moles, and our desired unit, which is atoms. And now looking at Avogadro's number, I know the 6.022 times 10 to the 23rd atoms goes in the numerator, and 1 mole goes in the denominator. This conversion factor, again, we never want to use that for our sig figs. Think about that conversion factor as an infinite number of sig figs. So the value we want to look for is our measured value, our given value for our sig figs. We have 3 sig figs here. And so in our answer, we should have 3 sig figs. This is a multiplication question. So we're multiplying 3 sig figs by an infinite value of sig figs, 1.48 times 10 to the 24. Don't forget your unit, copper atoms. There's our answer, 3 sig figs. We can go the other way and calculate from grams all the way now to number of atoms. Very, very cool. Let's go back to our periodic table and get that helpful, useful information piece. Where is it? There it is. Copper, 63.55 for its average isotopic mass, which means 63.55 grams per mole. So let's go ahead and start out. We never want to start with a conversion factor. We always want to start out with our given measurement, 3.10 grams of copper times, well, I want to get to atoms. How do I get to atoms? Through the mole. So 1 mole of copper over 63.55 grams of copper. I can keep going with my conversion factors here. I want to get to particles or atoms, 6.022 times 10 to the 23rd atoms of copper, Cu, over 1 mole of copper. Notice how, again, as chemists, we like to abbreviate. MOL is the abbreviation for mole, because why write 4 letters when you could just write 3? Make sure that your units cancel. Grams cancel, moles cancel. We're left with atoms. Lovely. So we would do that calculation. 2.94 times 10 to the 22 copper atoms. Now, fun fact, the original 1982 or earlier penny was actually mostly copper. Now it's not. Now it's copper plated and it's zinc on the inside and some other alloys. But if you have any original, before 1982 copper pennies, they averaged weight 3.10 grams. You now know, party fact, 2.94 times 10 to the 22 copper atoms are in that penny. How cool is that? You're gonna dazzle your friends the next party. 3 sig figs, just to emphasize that sig figs are always important for us in these calculations. Again, conversion factors, infinite number of sig figs. Don't ever look at those. Think about them as an infinite value sig figs. They are an accurate number. So just look at that measured value. Excellent. We'll again do more in class with those. All right, just a brief introduction. We're moving into energy, chapter E. E.6 is what we're really going to be looking at here. Overall, just a couple of definitions and a couple new conversion factors in order to be able to work with those throughout the next couple chapters. Energy in the universe is conserved, and all matter has energy. These are laws of energy and laws of thermodynamics that we have. We go into those more in depth in Chem 150. So if you take Chem 150, you're going to see this overarching idea again. What I would say just for right now, we'll use some of these factors once we get into movement of particles in Chapter 10. Right now, what would just be important is some definitions and seeing what parts of physics do we bring into chemistry. The two main ones are looking at the idea of kinetic energy versus potential energy. Kinetic energy is associated with movement. So this right here, the actual movement of the weight after we throw it off the building. We have a calculation with that. This should be squared. Kinetic energy is equal to 1/2 mass times velocity squared. So the mass itself contributes to the kinetic energy and the actual velocity of the object. We will again see this calculation in Chapter 10. Potential energy is the energy associated with position or composition. We can think about this as bonds, bond energy, also sometimes called chemical energy. We'll get into bond energy a little bit once we start building up our molecules. A lot of bond energy is not utilized again until we get into thermodynamics, which is Chem 150. Now, energy can be converted from one form to another. So chemical energy or potential energy can be converted to movement energy or mechanical energy. Such as solar energy can be used to be converted into mechanical energy. So we can interconvert between these two. Energy cannot be created nor destroyed, but it can be transferred. Just like our law of conservation of mass, we have almost the exact same law, the law of conservation of energy. In terms of some energy terminology, when we get into the first law of thermodynamics, that all matter possesses energy, we will be able to again see not only can we change from kinetic to potential, we can also change from a reaction or a system to the surroundings. So a system is really what we study, the actual chemical reactions that we have. And we can see that around us are called the surroundings. That's where we are. We're not part of the reaction, hopefully. We might get it on us, but we are part of the surroundings. And so what the biggest idea here is that the system and the surroundings can exchange energy all they want. Most often what we see is thermal energy, right? We can see that reactions could heat up. That's them releasing heat to us. We could see reactions cool down. That is the reactions taking heat from us. And so they get colder. Now, when we think about the universe, that is everything, the system and the surroundings. Again, we won't discuss the universe until we get into thermodynamics a little bit more in depth next semester. What we want to know is that thermal energy, the direction of heat flow. Heat is a type of energy, it's a thermal energy. And it's one of the most basic types of energy that we will see in this semester. Endothermic, if you think about that root endo, think about in. So I want to think energy in. Endothermic reactions take heat from the surroundings into the system. This is normally when we, the surroundings, feel a decrease in temperature. We feel the reaction getting colder. That's not that the reaction is releasing heat and getting colder. It's the reaction is taking our thermal energy and it's utilizing it in some way, shape, or form, kinetic energy. And so therefore, the surroundings are actually feeling that temperature get colder. Exothermic, we can think energy out, exiting the system. heat is transferred from the system to the surroundings. This is when we feel things get hot. There are reactions that are endothermic or reactions that are exothermic. Most reactions fall into one of these categories. Very few reactions have an overall thermal energy change of 0. They might be very, very small that we might not feel them, such as dissolving salt in water. That process, we might not see any change in the temperature because it's so small. But dissolving salts in water, specifically sodium chloride, potassium chloride, and a metal with a halogen. We'll talk about all of our periodic table stuff in a little bit. Most of those are endothermic. But when we boil pasta, we just throw the salt in and we don't think about it. But in reality, very, very tiny change, very tiny, something that we probably wouldn't be able to measure in our kitchen. However, still good to know. What we get from energy units are our energy conversion factors. Most often in chemistry, we will use the joule. The joule is the amount of heat that will change the temperature of 1 gram of water by 1 degree Celsius. All of these conversion factors, whether you're dealing with calories, the kcal, which is our dietary calorie, or joules or kilojoules, all of these conversion factors will be given to you. When I'm looking at conversion factors, I don't want you to memorize them. There will be a few things that I want you to memorize. Prefix multipliers for one. So the kilo, I want you to remember. We'll use it a lot. This one, though, you should know. Kilo as our prefix multiplier. 1 kilo, and we'll just use joule, is equal to 1,000. It's that 1 to 1,000. And so if you have to review those, go back over our SI units and review or introduction video. Not required if you've taken this class before, but if you're brand new, that's why it's required in the lab.